Hi, this is lecture video 4-3 for ECE 1220 at the University of Utah. I'm Professor Verkler, and today we're going to be talking about Boolean algebra. So we've been talking about logic gates the last few days, and then also the idea of digital logic where everything is ones and zeros. And now, instead of using logic gate symbols, we're going to use math symbology to represent the circuits. So there are many different ways to represent and, or, and not. And we call these the Boolean operators. And I learned actually using these ones right here, which come out of programming languages. But the textbook we use in the next class for this topic, for digital logic, uses the multiplier and the addition and the bar over the variable to represent the not of it. And so you can use either of these in class. I will accept either notation. And then sometimes in more like math-based classes, you might see these unions and things like that down here instead. So again, I'm showing this to you to make you aware that there are many different symbols to represent and or not. And so you may have seen different ones before, but these are the ones we'll be using in class. Let's talk about this. We have many years of using language to express logic, and so it's often useful to draw on your language skills when trying to figure out Boolean expressions. So for example, if we said A and B are true, notice we have an and here, right? So if A and B are true, so that means A and B with that exclamation point. And then it says or A and C are true, so that's A and C, and then we're taking the or of that. So that would become a plus sign right here. Or if you had written it the way I had been taught it in school, right, it would have been A and B or A and C. And you can put these in parentheses if you want, if that's helpful to remember kind of which ones happened first. Okay, let's do some more examples. So here's a network of logic gates, and we are going to find a Boolean expression to represent this logic network. Okay, so let's trace starting from the left. Here's our inputs X. And X went down here. So we've got an and, an or, and then two nots here. So if I look at this top one here, I have X coming in as one input. So I'll just start writing that. And then I have Y knotted. And they're going to be anded together. So I could say and not Y. And similarly down here I have a separate thing going on, right, which is going through the not X and Y. Then finally the output of each of those, so that's why I put in parentheses, the output of each of those is an or. So then I just put an or right there in the middle. Okay, now if I use the notation for the next upcoming 3700 class, it'll be X multiplied by Y with a bar over it to say the not, or, which is done with a plus sign, and then not X, so the bar over the X multiplied by Y there, and that multiply symbol means and. Okay, let's do another example. We can also create a Boolean expression from a logic table. So here's the logic table for an XOR. And notice it has a 1 when these two things are true and a 1 when these two things are true. So there are many ways we can create a Boolean expression from a logic table. And I'm just going to teach you one way in this course, and you'll learn more ways in the future digital logic class, which is ECE 3700. by the way. And a lot of our problems this term, our homework problems, are coming from the textbook for that class, from their like first 2 weeks of lecture. So how I like to do this is I look at wherever there's a 1 at the output and look at what you needed for an input. And I AND the inputs. So here I needed a B to be true, or I needed A to be 0. So A being 0 is the same thing as not A. So I say for this row, I want not A and B. Whereas for this row, I want A and not B to be true to get a 1 out here. And so then for the whole entire table, that means that if I have not A and B, or this other case, A and not B, if either of those is true, that's what the OR means, then I'll output a 1. And in any other case, I'll output a 0. Okay. So Boolean algebra has a lot of properties, just like math, and we've learned rules about how to add and divide, etc. There are similar rules for Boolean algebra. Luckily, the rules are pretty similar to the rules we have for math multiplication and addition. And so the fact that we use a multiplication for and an addition for or works out pretty well, that we can just call on our old math properties. So you can think of the nots here acting like negatives, right? If I take negative of the number -5, that becomes a +5. So same thing happens for knots. 2 knots make it true again. And so I drew it this way to kind of show they cancel, but we could have drawn it, I guess, this way. That's better for you. But I like seeing how I can like distribute in those exclamation points for the knot. And then just like multiplication, the order doesn't matter. And I can change where the parentheses are, just like current multiplication. And then distribution works like this. Same as with multiplication, as you learned growing up. The one caveat is I can't just distribute a knot like that. So that is where De Morgan's law comes in. I think this is the biggest one you need to be aware of because it's the biggest change from how normal math works. So when you distribute a knot, you have to flip the logic inside the parentheses. So if I want to distribute in this knot onto each of these, then that means that the logic function I had to change from or to and when I pulled the knot inside the parentheses. So let's see that again over here. I pulled the knot in onto each of those A's and B's individually, and in the process of doing that, I changed and to or. So it goes both directions. And so this law is useful if you're trying to simplify a complex Boolean expression. You may pull in a knot to be able to cancel it because there was like, oops, because maybe there was a knot in here you wanted to cancel it with. There are reasons like that you would want to pull it in to simplify the expression. Okay, so let's do one final example showing you how to simplify that expression like I just said. Okay, so in this case, right, I find it easier to write the knots and remember how they're, so I can see the distribution in easier, but you can do it using this notation if you prefer. So there we go. That's the equivalent expression to that. This is just different notations. And so I wrote it this way so I could see me distributing this knot. So when the knot goes inside, I have to use De Morgan's law and say this is going to become not A, oh, sorry, there should be an and symbol, or not B. So then the knots simplify away, right? They cancel each other like 2 negatives. So I get A or, and these two also cancel each other, B. So this expression is actually equal to or. And I think with that, you now have the skills you need to solve worksheet 4-3.